Lots of names. Last year's PPS, even weirder names than this. What's going on? Why is it?
Yeah, I think it's when people.
Not from here. Something. Oh, the projector's playing. Last year, the chair tried to pronounce all the names, and it was like a wrong choice from the beginning. Yeah. No.
Maybe Cătălin yesterday made me notice that I pronounced badly his name.
Hriţcu, right? Hriţcu. Oh. Oh. Yeah. Cătălin. Researchers at INRIA. Umbrella term. I cannot pronounce half the names. Where's the mic? Ah, you have mic. Of course. I have the... No, this is for recording. I will have this to talk into. Yes.
Okay, so but he has to use these.
I have to use both.
Yes.
Yeah. So make sure you tell that to the other speakers as well.
Okay. Okay, let's start. Are you ready? Hello everybody, welcome to the session of probabilistic programming. We will have 4 exciting talks. The first one is by many people, and it will be presented by Li-yao, and it's about a language for property-based generation.
Hi, I'm Leo, and I'm going to talk to you about LUC, a language we have developed in UN in collaboration with researchers at INRIA and Chalmers. So, at a very high level, LUC is a domain-specific language for writing programs that produce random data, satisfying some complex predicate P. The user can use this DSL to exercise fine control over the distribution of generated data, and they do that by lightly annotating a predicate. So, but first, let's take a step back and see the problem we're trying to address. How does one find bugs in large software artifacts? And by large software artifacts, I mean things like GCC or GHC. We could try using exhaustive testing, but for large enough artifacts, we would wait a bit. Some state spaces are just too large to exhaustively explore. On the other hand, we might try using random testing. And this has been successfully used in the past. For example, there is the C-Smith work, which found over 400 bugs in C compilers. There is the work by Palka et al. That found bugs in GHC by generating well-typed Haskell programs. And there is our own previous work on testing non-interference. So, what exactly is property-based testing? Property-based testing takes a universally quantified property of the form for all x q of x. You can think, for example, that q is the property that reversing a list twice yields the original list. In a property-based testing tool like QuickCheck in Haskell, to test this property, we would generate x's and test that the property holds. While this works very well for a very large class of properties, there is one particularly interesting class that it does not work as well, and that is conditional properties. An example of an interesting conditional property is progress. If a term is well typed, we expect it to be either a value or take a step. In order for QuickCheck to test this kind of property, we would first generate a value for x, proceed to check the precondition p, and if it holds, proceed to test q. However, if p doesn't hold, we would discard x and start all over. This is clearly inefficient and does not lead to good testing. Now, what can we do to make this better? Well, for one, instead of viewing p as precondition, we can view it as part of the quantification itself. So instead of generating x's and filtering them using the predicate p, we can instead only generate x's that satisfy directly, and then proceed to test q. Now, this works well, but it raises a question. How does one generate these x's? And more importantly, with what distribution? Perhaps we could use a uniform distribution and ignore this problem, but the answer is we can't really use that. And to tell you why, I will introduce the first running example I will be using throughout this talk, which is borrowed from the non-interference literature. Now, we have two labels, public and secret, denote public information and secret information. And we will say that two pairs of labeled integers are indistinguishable if the labels are equal, and if the labels are public, the integers are equal as well. So, for example, one public is distinguishable with one public. 17 secret is distinguishable 42 secret, but 17 public is not indistinguishable 42 public. Now, let's see what a distribution of uniformly distinguishable pairs means. This is a representative slice of the possible state space of indistinguishable pairs, where all pairs have equal labels and their first integer is 0. So we have 0 secret, negative 42 secret, all the way to 0 secret, 42 secret, and 0 public, negative 42 public, all the way to 0 public, 42 public. Watch what happens if we filter this space using the indistinguishability predicate. The only indistinguishable elements that for every indistinguishable pair that has a public label, we have 85 pairs here that are secret. Imagine extending the domain from 42 to 32-bit integers. We have way, way more secret pairs than public, and that cannot lead to good testing. In fact, in our own experiments with indistinguishability, what we found out is that the distribution we require will have a roughly equal amount of secret and public information. And that makes sense at an intuitive level, because we want to have enough secret data so that can leak some secrets, but we also want to have enough public locations in our machines so that we can leak the secrets in too. Now, but the fact that this is the distribution we want raises the question, how do we generate this? And we do that using what is called a custom generator. In Haskell, for example, using check, we can write a custom generator that produces the distribution I explained. The way we do that is we first generate an arbitrary label, public secret. We then generate an arbitrary integer, x1. And then, if the label we generated is public, we make sure that the second integer is equal to x1. Otherwise, we generate a second arbitrary integer. So this way, we generate an indistinguishable pair with the desired distribution. A natural question to ask is, how does one write such custom generators? In this case, it was relatively easy. In general, how does one write a good generator given a precondition p? And by good, I mean all generated values must satisfy p, so that we don't waste any effort by discarding. All values that satisfy p can be generated, so that we don't miss any potential bugs. And the distribution is somehow appropriate for testing. It's interesting to note that while these two properties are fully formal properties, we can sort of soundness and completeness with respect to p, this one is slightly more heuristic. But in general, this is not really a problem. Like, writing custom generators has been a thing for many, many years, since 2000, that John Hughes over there and others created QuickCheck. And we can use the full power of a language and a library like QuickCheck to find such bugs, to write such custom generators. And there have been many success stories, like the ones I described in the first slide, where this has been successful. In my mind, the real problem with the custom generators approach is maintainability. If you think about it, generators and predicates are distinct software artifacts that are supposed to be two sides of the same coin, which must be kept in sync. In the course of a large testing project, these artifacts will get out of sync, and this is a very source of bugs, which we found a hard way when we were playing with random testing ourselves. The maintainability problem also has itself a rather natural solution. let's derive generators automatically from predicates. But the real question is, how do we do this? And this is what Luck addresses and what I will focus on in the rest of the talk. So, in the rest of the talk, I will briefly explain two other approaches, two existing approaches for deriving generators automatically from predicates, each one with complementary advantages and disadvantages. And then I will describe Luck, which synergistically combines these two approaches to derive generators automatically. Let's see narrowing first. Narrowing is a concept borrowed from functional logic programming and can be thought of as an incremental generate and test. Instead of generating every variable at the beginning and just filtering the generated values using a predicate, we instead instantiate every variable at the first location where it appears. For example, if we use our indistinguishability example, we would first generate L1 and L2 to be equal. Then we would check L1, and if it's public, we would generate X1 and X2 to be equal again. Note that this behavior I just described is exactly the generator I showed you earlier in quick check. So this approach is a very lightweight approach and allows for a very, very elegant control over the distributions, as I will point to in a bit. However, it is not always efficient. And to see why it's not efficient, I'm introducing a second example, binary search trees. Now, this is a standard binary search tree predicate in Haskell. Empty trees are always search trees, and nodes are valid search trees if their payload is between appropriate bounds, and the left and right subtrees are also binary search trees of appropriate bounds. And I want to focus on the constraints on X. Now, for simplicity, assume that low is 0 and high is 17. Following a narrowing-based approach, we would instantiate X at the first point where it appears, namely at the constraint low less than X. So we would generate a positive integer, for example, 42. But then, when we encounter X less than high, this is a check, which can fail, and there is a large probability of backtracking. Now, there's another approach that doesn't suffer from backtracking, namely constraint solving. And here, I'm talking about constraint solving both in the form of generating inputs directly from predicates and about symbolic execution. As I already said, this approach doesn't suffer from at least observable backtracking, but it has a different problem. You do not have predictable control over the distributions. At best, one can get some uniformity guarantees, but as I hinted at earlier, the uniform distribution is not always appropriate for testing. Moreover, the potential overheads associating with keeping track of constraints can be an overhead if narrowing just worked, like in the indistinguishability example. So the complementary strengths and weaknesses of the two approaches led us to design Luck. The goal of Luck is to give the user control over where constraint solving happens and to give the user control over distributions in the style of quick check. And to show you that, I will show you an example of a Luck program. Modulo minor syntactic differences, there are two main things that are different between this and the previous BST program. The first one are the percent annotations in the branches of the case. Now, these work like a combinator in quick check called frequency, which means that when we are going to generate a tree, 1 out of size plus 1 of the time will generate an empty tree, while size out of size plus 1 of the time we would generate a node. The second thing is this bang annotation here, which we call an instantiation point. And that controls where exactly a variable is instantiated. So, for example, if we were going to encode a narrowing-based approach, this bang would be exactly after the first constraint on X, namely here. So, let's see what happens by moving the bang after both constraints. Imagine again that low is 0, high is 17, and X now is associated with some domain like -42 to 42. When we encounter the first constraint, the domain of X is filtered down, so now X can only be between 1 and 42. Then we encounter the second constraint, X less than high, and the domain of X is further refined. Finally, we sample from the domain of X, and no backtracking is necessary. Everybody's happy. So we implemented luck, and we replicated successful experiments of the past. So we tried to generate well-typed lambda terms to test GAT, and to generate indistinguishable abstract machines to test interference. What we found out is that with significantly less code and effort, we were able to achieve the exact same bug-finding performance and find the same bugs that the other two case studies found in terms of test per counterexample. So we achieved the same test counterexample at the cost of around an order of magnitude in efficiency. Now, to quantify what I mean by significantly less code and effort, one of my favorite anecdotes of this whole slide is that the Palka code is accompanied by a comment at the top of the file that says reading the code is not recommended, followed by 1,600 lines of fairly complicated Haskell. In contrast, our luck generator for the same thing is around 80 lines of just encoding the type checker in luck. So, yeah, we're happy about that. So, since I have a tiny bit of time, I want to give you just a taste of the semantics of luck. Recall that what we want to accomplish is give the user control over where narrowing and where constraint solving happens. So, we would like these two terms to have different semantics. So, we would like our semantics to be able to distinguish between the locations of the instantiation point. Intuitively, the first one does potentially more work, while the latter has a higher chance of backtracking. Now, this is the form of our judgment. It takes as input an expression and the target pattern P, which usually will be true. So imagine if the expression is a predicate, this means that we want to generate values that satisfy the predicate. And it also takes as input a set of valuations. For example, the domain that we saw before for X, negative 42 to 42. The outputs of our judgment are the probability of the result and a resulting set of valuations. In the resulting set of valuations, we have removed unsatisfying valuations from the input. And since there might be no satisfying valuations in the input, the result might also be nothing by negative. Now, let's walk through the example that we saw before. 0 less than x, x less than 17, instantiation point at the end. And we want to generate things that satisfies predicate when x has the domain negative 42 to 42. The first thing we encounter is the 0 less than x constraint. And then, with probability 1, the result is a domain where x has values between 1 and 42. Then, we proceed to the second conjunct, and again, with probability 1, we further refine the domain of x. Finally, we encounter the instantiation point, and we have 16 equiprobable derivations, each one with probability 1 out of 16, where x has a single value between 1 and 16. Now, imagine moving the instantiation point after the first conjunct. So we encounter again 0 less than x, like before. With probability 1, we have a domain 1 to 42. We encounter the instantiation point, which now leads to 42 different derivations, each one with a smaller probability than before of x having 42 different values. And now we feed each derivation into the second conjunct, which means that with probability 1, 16 of derivations would just return the input unaltered, while the rest will fail because this is not satisfied. So if we gather everything up, 16 derivations succeed with lower probability than before, and the rest 60% of the time we fail and need to backtrack. And this is exactly what we want to expose to luck programs. Now, a bit about the formalization of luck. It might seem like all we do is play with integers and linear constraints, but in fact that couldn't be further from the truth. Integers and booleans are encoded as algebraic data types in a lambda calculus core, and all the semantics I've shown you are derived by this encoding. We have formalized this core in Coq, and we have proved soundness and completeness of the language. So what these are the two of the properties I showed you early on in the talk. So every value that is generated satisfies a predicate, while every value that satisfies the predicate can be generated. So these are the two properties we have formalized. And to conclude, I've shown you a language for writing artifacts that serve as both a predicate and the generator. And we allow the user to write lightweight annotations which give him control over both distribution of generated data and the generation strategy used. Thank you.
So we have time for a question. Unfortunately, we had a technical problem, so we have only one mic. And either you speak that or I will bring it. I like your question. Can you write the slide where you explain how to generate the trees which are binary subtrees? So my question will be, it looks like you do some backtracking when you generate the tree based on the size, but the low and high, for example, if you choose to have X you want, for example, and you do binary search tree on the first stage, you divide the size by 2, but you'll have no tree at all that will be able to generate. Then the element choice between 0 and 1. How do you do this?
Yeah, so then you would backtrack and return an empty tree. So there's backtracking. Oh, am I here? Yeah. So there are 2 points where it can backtrack. It can backtrack here, which is a partial instantiation point. So you would choose to generate a node, then fail and backtrack to return an empty tree, which is a valid tree between 0 and 1. And the second backtracking point is there.
So what I mean is that when you divide size by 2, when you start with size 42, for example.
So size 42 is an upper bound. So it's meant an upper bound, not as an exact bound.
Yeah,
Yes.
that means that 20 times out of 21, you will have to backtrack.
Oh yeah, yeah. That's a. It depends on the choices of these, right? If you want to generate basically empty trees, providing 0 and 1 here, then yes, this is not the generator you want. Yeah.
So how do you deal with predicates to use temporary data structures? So for example, you want to create graphs that are connected.
We haven't experimented with graphs yet. Most of the data we have generated are largely trees, well-typed terms, lambda terms, abstract machines. All of that are tree-like structures, so there are no cycles there. But I'm assuming there are some very fancy predicates we were able to encode here. For example, imperative programs that have loops in them, and you can sort of see that it would run the same techniques, something like a generation by execution strategy, which allows you incrementally generate your instructions that have potential loops, would work to generate graphs that have potential edges backwards to your structure. So I think it could be possible, but I haven't tried it.
There's a nice talk at the panel on Monday on Boltzmann templates. Trying to deal with exactly generating type lambda terms, but they want to generate a uniform distribution. And it turns out that's hard to do. So what sort of distribution do you get?
Yeah, so you can encode Boltzmann samplers in Mach, and it's a very natural way of doing. So basically, to use Boltzmann samplers as a very short summary would be you systematically choose the parameters r and r prime in the branch of a match. If you choose them systematically based on some generation functions theory, you can actually get a Boltzmann sampler effect. The point is, you don't always want a uniform distribution. And we have established techniques in the random testing world where you collect statistics about what distribution you generated, and then tweak it if you want better testing to use it by tweaking these weights. So while we don't have a closed form representation of the distribution that you get in the posterior, like one would do in probabilistic programming, we do have ways of obtaining statistics of the resulting distribution, And we can use that to tune our distributions to find bugs. We don't really care about what distribution we get as long as we find bugs.
So for the example you gave, testing the Haskell strictness optimization, do you want the uniform distribution?
No. In fact, it couldn't be further from it. I think 1/4 of the terms we generate are seeks to force strictness because we're trying to find strictness analyzer bugs. So we're trying to include a seek function wherever possible to force things.
So it's just sort of hack up?
Yeah. It's heuristic. You collect statistics, see what you want to generate more of, and try again.